us to talk about remote and rural electrification. I guess I should have given that a little more thought when I wrote out the agenda to have something a little easier to pronounce, but that's my bad, so special treat for you guys. Let's talk about what we want to cover today. Okay, so I wanted to cover some definitions. Wanted to talk a little bit about kind of in the beginning of this type of application, what did we see, and I'm going to try to spend the bulk of the time this morning talking about some design considerations. So as I was going through my material for this week and trying to whittle this down to 45, 50 minutes and have some time for questions, it proved to be really hard. There's so many design considerations and there's so many trade-offs and there's so much to talk about on this. So I've done my best to kind of cull this down to something that we can get through in 50 minutes, something that's meaningful, that gives you some, again, considerations and things to take into account. I've got a ton of stuff on this. I've got webinar slides, I've got PDFs, I've got white papers, I've got decks from suppliers, etc. So by all means, if we whet your appetite in what we're going to cover today, please follow up with us. Either via the tech line to me or as a follow-up on the survey. Let us know you're interested in hearing more. If you've got a project specifically, let's talk about that. And yeah, let's just share information because this is, for me, this is a really interesting application and don't see a ton of them, but the ones that I do see are very intricate, very detailed, and just a lot of thought goes into these. All right, so lots to cover. Let's get going. I call this application types, but really what I'm trying to get at is definitions here. So if we think about all of the possible projects that incorporate solar, and then we limit those down to those that only incorporate solar plus storage, and then we further specify that, okay, we're only talking about off-grid or permanently islanded systems. One of the applications in that basket or in that Venn diagram would be rural electrification. So what do I mean by that? I mean, one or more, usually more, many residential buildings, dwellings isolated from a grid with a local grid form, typically using at least one renewable energy source and typically using some kind of rotating generation, a genset essentially. Typically the genset's introduced as it's the most, perhaps it was at the time, the most reliable energy source. It's hard to beat the energy per, the levelized cost of energy in some respects. It's also tough to beat the energy density of the fuel itself. And it can be a great backstop if you're talking about the right kind of use case and the right kind of days of autonomy trade-off versus system size. So what I'm really not going to cover too much today are the following. Microgrids, and you might have some overlap here with energy service companies. I'm not really going to talk about diesel offset too much. Really want to focus on more, the kind of residential mini grid type of approach or residential microgrid. So I said I wouldn't cover it, but I've got a slide on it anyway, because I think this is super interesting. Diesel offset as an application. So these are a couple examples from Schneider Electric and from SMA on essentially what's, a Modbus SCADA approach to using PV to optimize the amount of generator runtime in a microgrid. We see these a lot, or when we see these, it's typically as a, I shouldn't say typically, it's frequently as a military type application where they've got dedicated generator runtime and they maybe just want to optimize how much they use it, how hard they load the generator, when they let it idle, etc. And these can be very cost effective, and part of the non-cost value prop, I suppose, is optimizing the fuel savings. Of course, there's a renewable aspect there, but also we see in some of these applications, the fuel itself becomes the risk in the operation, and specifically the supply chain to get the fuel to the site So if you can minimize that fuel spend, there's some great kind of non-cost outcomes to that. So I said we wouldn't cover that too much. I'm going to keep rolling. Again, what we're not going to talk about, but I'm still going to cover it, would be more of a commercial microgrid approach. So this is a screenshot from a great white paper from Schneider Electric that was actually just published in a Green Tech Media write-up as well. So functional architecture for a commercial microgrid or industrial microgrid, and the different layers of technology it takes to get there. To sum these up, these are going to be buildings or campuses. You might see customers anywhere from an arena to hospitals to resorts, kind of multiplexes that incorporate a variety of sources, a variety of different control layers to couple the system to the grid when appropriate, decouple it and run it off renewables when appropriate, have a generator source when appropriate, and all of the different layers and intelligence that goes into optimizing that. Not going to cover that too much. It's kind of beyond the scope of what I'm skilled to talk about, but lots of great resources out there. So again, getting back to what I really wanted to cover around remote and rural electrification. Start talking about design and considerations. So I like bringing this slide up because it's hard to overstate this. So in a grid-tied system, we're generally talking about production averaged out over a month or a quarter or a year. We're looking to offset energy. We know we've got a backstop of the grid, and if the system fails and the grid's up, the lights are still on. That's not that's not an unrealistic situation. Off-grid, if the system fails, you just don't have that energy, and you don't have the ability to run whatever the load was that you were contemplating in the first place. So, in a way, when we talk about storage as load shifting, I think the original off-grid, and I know a few of them, advocates and trailblazers, they lived load shifting because they had no other choice. There were things that you just couldn't do at night because it was too energy intensive. The conditions weren't right, et cetera. So, again, for off-grid sizing, really what we're talking about is, down to the single load, the single plug analysis on what's being run, what's the watts, what does the load profile look like, what's the duty rate. These are things that are all going to go into account in sizing this system. So the load analysis cannot be overstated. Typically, I put this slide at the end, but I think it's really useful in bringing up at the beginning. There's some great software that will help you design and simulate some really advanced systems. On the left, Homer Pro, this has quickly become the go-to resource for large microgrid, large mini grid modeling. Allows you to do some really interesting stuff with lots of different fuel sources. Energy Toolbase, going to be used more for typically your grid tied analyses where you've got particular rate schedules you're looking at. But it's my understanding there's some good off-grid modeling that's capable there as well. So I wanted to plug those at the beginning as we walk through these. I usually put them at the end, and I feel I've been doing them a disservice over past couple months. So again, in off-grid sizing, everything's driven around the loads. That's going to dictate a couple things. So the total amount that you use those loads is going to dictate how much storage and how big your array needs to be. How often they coincide and how high that drives your peak is really going to dictate how much inverter capability you need in terms of peak kW or kVA, depending on what you're running there. And then the final thing, knowing your environment. So how many peaks and hours do I have? What kind of seasonal factors do I need to take into account? And the environmental piece, really is going to dictate what assumptions you make on days of autonomy. And that's going to be a key driver when we think about fuel sources versus storage, and how do we pick the right equipment and make the right assumptions on how often we're going to use them. So I'll keep going on the kind of information we need to gather, and it's so it's a couple big buckets here. The daily consumption in watt hours. So how many total watt hours am I going to have? Is it something I can I use the analysis term peanut butter sometimes. If I know I have a total amount over a total period, do I just kind of peanut butter spread that amount over the period and average it out, or do I know there's going to be real big seasonality here? Seasonal driven loads, heating and cooling, obviously. Occupancy is occupancy or usage the same seasonally? Are there big types of things that happen each fall related to, I don't know, agriculture or harvest or process that needs to go on? These are all things you need to take into account. You can be like me and try to do them in Excel. You can use a great tool like Homer. There's some good things, but I think a lot of this is going to be grassroots and home brewed as you put these load profiles together. From the consumption, we got to think about peak load in terms of watts and characteristics. So the sum of all loads that will be on simultaneously is going to drive the peak. I've got a note in here: separate AC and DC loads. If we're talking about a rural microgrid, and we've got a barn, maybe a couple cabins, maybe a central building, lodge, office, school. Think about how often those can be run simultaneously. Think about AC and DC loads. Depending on if there's any process or anything like that, maybe that's things that can be done in a DC load, gates, lighting, etc. That can save on some of the equipment sometimes. Voltage and frequency the loads require. So we see this sometimes in these larger projects where we're incorporating process equipment, compressors, tools, motors, etc. Don't assume that those are nice clean profiles with good power factor and no harmonics. If it's brand new equipment, you can pull some of that information from data sheets. If it's older equipment, make good assumptions, make conservative ones, get real friendly with your fluke meter, all those types of things, because the power factor can really be your enemy pretty quickly on some of those loads when you get towards the higher end of the system sizes that are capable of being put together. The difference between a 0.95 power factor and a 0.8 gets to be a really high portion of your total kVA from the system. So again, I'm not an electrical engineer, but it's something I think that people miss a lot of times. Days of autonomy. So this is something you'll need to quote unquote collect, but really it's going to be a trade-off you're going to make from this point all the way through the end of your design process. Not so much in how many days in a row will the loads need to run with little or no sun, but how do you account for those circumstances? So typically when we talk about days of autonomy, we're trying to get around how long can we keep the loads on with no renewable source? So with no PV, if you're using wind or water and there's no wind or water available, how long can you make it without that? So combination of using a generator to bridge that gap, or just adding more storage. Don't neglect to account for snow. So great point there, that when the sun finally does come out, how long does it take to melt the snow on the modules and begin producing again? Okay, and then you also have to think about sun hours during the darkest months. How much, again, we'll go back to the loads, how much is it impacted by loads? Are you gonna have coincident loads plus lack of harvest, or is it not occupied if the load's lower? Typically, if we're talking about occupied buildings, you've got to figure out some way to bridge this, either as a secondary fuel source or just having a whole lot of PV headroom. I wanted to introduce a couple points here and think about not just thinking about loads as a static or a dynamic at the time the analysis is done. So think about a couple things here. Loads are going to drive a combination of PV and storage sizing. The concurrent loads, and what I mean by that is the loads that occur during the hours of production. So those are going to drive inverter capacity. Non-concurrent loads are really going to drive storage needs. So how much are you shifting that load from a production time to a usage time? How much of that do you have to bridge? Also think about current and future loads. And what I keep coming back to on this is I had the pleasure of going with some colleagues to Brazil in, well, that's been a long time now, 2014, to work with some partners down there on some storage products and kind of marketing platform stuff. And we had a brief conversation with someone who was putting together a true rural electrification project in the Amazon area, well, an area of the Amazon that was typically tribal land, and a lot of the locals had moved away to nearby cities because there was power, there was convenience, comforts, etc. And they said they'd experienced in the past with similar projects a phenomenon where once they electrified the village, people came back, and not only did people come back, but they brought loads with them. Really the ability, the supply drove the demand in a way. So when people came back, they brought cell phone chargers, they brought small TVs, etc. And the system had no way of dealing with those excess loads besides taxing the batteries more heavily and browning out large loads. So if this is something where electrifying whatever it is you're talking about is going to increase the demand beyond what you can measure at the time, that's something you've got to account for. And that's easy for me to say in my marketing slides here. You've got to account for that. You've got to come up with some combination of the following: A, estimating what you think the increase is going to be and building the system to that. Or B, coming up with a system that will, and this is a lot harder to do, via control software, et cetera, that will limit and shut down loads and curtail loads to keep the system operable. What the project ended up encompassing at the end was a pretty advanced metering system where they metered, I think, daily kilowatt hours, and they would open some contactors and things, and essentially depower some of these cabins if they went beyond their daily maximums. So also think about where are the loads when you're starting to talk about a multi-cluster, a multi-nodal system where you're going to have distribution points that are tied together. You can start to think about where are the loads. Do I site? Is it perhaps more cost effective for me to site storage locally versus tying the system all together? And what I guess what I'm getting at is I'm thinking about a small kind of communal living environment where you've got maybe a central building, a barn, you've got some cabins. It might be more cost effective to run more, smaller systems, to put real small PV plus storage, off-grid systems at each one of those cabins, and not aggregate them into the larger system. Similarly, if the loads are concurrent during the day, you may consider putting those as on the AC side of the system, and we'll get into that as well. Loads versus levelized cost of energy. Really, anytime that you're making your own power, you've got to do a lot of your own math on how important is that. Is it worth the, you may be in the 25 cent per kilowatt hour range. You may be in the 40 cent per kilowatt hour range. As you get towards when your system is really, lacking headroom, you're going to make those choices with a lot more thought behind them than you typically would. Okay, fuel sources. So I wanted to introduce this thought and to think about what's your levelized cost of energy on storage versus combustible fuel. And I didn't have a lot of data on this. I was interested. I dug up some I guess, from the educational sector, some white papers that talked about this, that compare a variety of different numbers from a variety of different sources. I mean, big grain of salt here, and I encourage you to do your own research if you're really contemplating seriously one of these projects. But you know, PV off-grid, so solar plus storage. We've got ranges here from, looks like about 18 cents a kilowatt hour to high 20s. For diesel off-grid with a storage component, you know, higher for levelized cost of energy, but a lot of that's going to depend on how often you're using that fuel source. Is this the fuel source that you're using for 12 hours a year? It's going to be a really high levelized cost of energy because you've got a fixed asset, you've got a maintenance, but you're not running the generation enough to amortize that cost out. Lots of things to consider, but as you think about designing one of these systems, you've got to think about all of the loads, you know, not at every hour of the year, but think about the load duration. So how many hours am I going to use this load or this technology or this fuel source, and you know, how much mix do I want to put on that asset? So in a way, you know, when you're thinking about some of these large systems, these are the same kind of decisions you would make as a grid operator. How much do I want to rely on this fuel source? Is from both a cost perspective, from a maintenance perspective, from an environmental impact, versus, you know, how much do I rely on, you know, renewables and storage? And I made the reference early in the presentation to thinking about, thinking about in the early days. I think we tended to rely on generators that were smaller for more hours a year. And I talk about this with Brad Bassett, who's been with our company for, almost 20 years now. And he said, really, the math is changing. And the first big breakthrough we had was a few years ago when we realized, boy, PV is really affordable compared to these other fuel sources and energy sources. And what I mean by that is wind, water, and rotating generation. That if you've got the land, if you've got the solar resource, it makes so much more sense just to add more PV to the system and really economize or optimize how much of those other things you're looking for. Now I think the second big paradigm shift is that storage is becoming more affordable, and we're better understanding how to use it. That's really optimizing how much we're using rotating generation. So I guess the takeaway here is these things are dynamic, and if I do this presentation again next year, the math could be different. We could be talking about systems with no rotating generation at all because we feel it's cheaper to add more days of autonomy on the storage side of the equation. So, I'm looking forward to having that conversation next year, hopefully. So we've talked about loads a lot. We've talked about fuel sources. I wanted to talk about architecture a little bit. So where to introduce the PV to the system. So I wanted to frame this as not an A versus B, but kind of a how do we have the right amount of A and B to make the largest sum. So typically when we're talking about AC, DC, or hybrid coupling, again, a lot of considerations that come into account. Load profile. So how often are these loads being used and when is kind of, how we would sum up load profile. Location. And what we mean here is not where is the system located, is it in Utah or Florida, and that's important too, but where's the PV resource relative to the loads, and sometimes you've also got to say relative to where we can put the storage. And I say those are three different things because, I can think of projects I've seen where the loads are going to be either outdoors or, in residential spaces, and that's not where they wanted the equipment and the storage. They wanted those, you know, in a basement or in an outbuilding. So anytime you're breaking up one or more of those things, it's going to be a consideration on AC versus DC coupling. Think about the usage of peak PV kilowatts to peak load kilowatts. And really what we're getting at there is you know, kind of your duty cycle. How often for an 8 kilowatt system, how often am I at inverting 8 kilowatts versus a much lower load? So how peaky is that load profile? Other available energy sources, is there a generator or some other kind of renewable that we're integrating? This is a big one here, retrofit or new installation. That will definitely sway the equation one way or the other. If you're integrating and you're retrofitting an existing PV system, you're obviously going to be predisposed towards an AC coupled system. Overall system size, of course, we've got to take that into account. And then is this something where we're either peak load shaving or trying to curtail certain loads to optimize the system? So again, this is not an AC versus DC coupled conversation. This is a how do we blend the right amount? And really, you know, where we end up is hybrid systems. So I've got here an Outback system. You could do the same thing with Schneider or some other equipment. But basically, how do we decide which PV goes into storage first, so DC coupled, versus which PV do we turn into AC because we're trying to consume it at the same time we're producing it, or we're trying to produce it in the same place that we're producing it. So it really starts to be a 3 or 4 variable equation, 3 or 4 variable, excuse me, a 3 or 4 variable equation. That's what I was trying to get at. From here, I wanted to speak to another continuum or spectrum, if you will, on aggregated versus distributed systems. So I tried to be as high level on this as I could because I think you could easily talk about this kind of paradigm for a couple of different components. But what I'm getting at here is how much are you aggregating the total inversion capacity? So you know, your total system size versus multiple distributed or disconnected systems. And then how much, we'll speak on the next slide to one big battery bank versus multiple. So on the aggregated inverter side, pros, allows for really large loads or large loads. If these are loads you're looking at that you can't disaggregate, meaning you can't say, okay, I'm going to use this load off of this panel and I'm going to supply that separately from this load. If it's a process, if it's a large, you know, refrigeration system, or it's a building that's just not practical to disaggregate, you're probably gonna have to go this route. Can facilitate larger and more cost-effective components. What I mean by that is, you know, possibly you can get a lower levelized cost of energy on a larger PV system or a larger generator or storage system with larger components rather than, you know, the diseconomy of scale. Cons. The interconnection equipment can be more difficult to engineer and procure. So there's great white papers on this from most of the major manufacturers on either they'll call them multi-unit systems or multi-cluster systems. As you start to introduce more and more equipment at call it a low voltage DC bus, the balance of system to be able to do that can be really expensive and can be difficult to engineer and procure and make sure you're getting what you need. And I'll try to speak to that in a few slides. Product availability. You know, if you are relying on larger, more cost-effective things, typically there's a trade-off there, and that comes with lead time or availability. And the last one I'll say is scalability. So if you know, if you're really designing on the bleeding edge and you're putting large, you know, 80 kW clusters together, you may not have a lot of headroom beyond that because of some of the practical limitations around monitoring a system like that. You know, the ZAN bus, Modbus, CAN bus, SCADA controls for some of these really large systems. And then just introducing, you know, say I've got an 80 kW system and I realize I've got more load, or I'm going to add one more building and I need 10 more kW. A lot of times you just don't have the headroom. On the distributed side, so thinking about things that are selectively interconnected or maybe not interconnected on a campus. Products typically more readily available. Like this is our bread and butter. So we're really dealing in this space here of we know every day how many Radians, XW Plus, Magnums, etc. we have available that can be out there sourced and shipped at short notice. Distributed systems can be scaled, I'll say, more easily as loads change. If you've designed a certain call it sub panel or building, etc. If you design that around a certain load profile and a certain usage, occupancy, etc., and that changes, you may be able to add another unit in parallel, add another string of PV, add a charge controller, add more storage. I say more easily because it's it all depends on how in what time frame are you making the increase or the changes, and what are the increases relative to the beginning system size. Some of the cons: more complex maintenance requirements. So if you've got a campus of 10 cabins or huts or classrooms, etc., and they're all running on different systems, that's 10 stops you've got to make. That's 10 things you've got to keep up and running. Granted, we see some really advanced monitoring platforms from some of the manufacturers out there that can aggregate those into a fleet, which can make that a little more easy. But you're dealing with fewer of something that's more complex on an aggregated system versus more of something that's less complex. It's a trade-off. Lack of scale can lead to higher costs. You're not going to see the same, you're not going to see the same project pricing. You're not going to see the same storage pricing, wiring, etc. Which I didn't really cover on the wiring side, but obviously as we parallel systems and we add more and more current, the balance of system cost typically comes on the current side. So something to account for. Talk about battery banks, single versus multiple. So on the left, we've got a design scenario, and we've tried to, a friend over at Schneider has done this for me. So on the left, a 300 kV amp hour, so kilowatt hour, let's call that, at 48 volt is 6,000 amp hour battery using 2 volt cells, so 4 parallel strings of 24 each. A single, you can aggregate all this and recommend, possibly some isolators here and things, but this is going to have a much different profile and kind of ease of installation as something on the right here. So where you've disaggregated these systems, you can disaggregate the storage as well, and now you've got what do we see here? 2 3,000 amp hour capacity banks of 2 strings each. Generally speaking, on the storage side, anytime you're talking low voltage DC, the amps add up really quickly, and that's going to sound tremendously obvious, but there's not a lot of easily found balance of system for paralleling these 4 strings. This is going to be, probably some custom busing. You're going to have a lot of protection that's going to need to go onto that. It may or may not be easily sourced. It's also going to limit your, expandability in the future. On the right side, you've got a little bit more of a challenge in monitoring something like this. You've got to figure out how to take 2 parallel monitoring streams and kind of combine them into a useful view. And there's trade-offs, right? In the right system, you're going to need to parallel those on the output side, on the AC side, to be able to power loads, and then hope that your charging parameters and that you're using those systems, call it, quote unquote, equally. wanted to think about some points to consider on the inverter or inversion side. Central location needed to connect wiring and install breakers. Anytime you're aggregating loads together, you're going to need distribution. So a load center, a panel board. If you've got DC loads, you've got to do that as well. Hopefully, it's obviously need to be separate things. And remember that almost all of these systems are for indoor mounting only. So yes, I suppose technically you're within your rights to take a really expensive system like this that's NEMA 1 equipment and put it in a covered carport, build a shade structure for it. But these are designed to vent, to have fans, and anytime they're open to outside influences, you're just dealing with shorter lifespan of the equipment. So almost always recommend a power structure or an outbuilding for things like this if you have to. If not, put them in conditioned space and enjoy the benefits of not having thermal derates. This should be obvious as well. A battery-based inverter can have a very large current draw, especially when the battery voltage is lower. Think about that, obviously in all your sizing and your overcurrent protection. On the battery inverter to charge controller, that can be some very expensive wiring. So under 10 feet is best. If you do need to site your array further out than that, you're probably going to want to think about AC coupling and kind of judge the relative trade-offs. I wanted to put in a word for pre-assembled power systems. This can really simplify the installation experience on one of these remote or rural sites. Anytime you're kind of standardizing the integration aspect, and what I mean by integration is the inverter to inverter, inverter to DC, inverter to loads connections, you're going to be better off. Pardon? I heard some noise on the line there. Okay, I'll keep going. Think about doing this. Think about standardizing the experience. I think as much as you can, think about what can you integrate or possibly containerize offsite that will simplify the on-site experience. Typically, we're thinking about these systems because they're not easily accessible. We're typically not thinking about these types of systems because it's a grid defection choice. We're typically thinking about them because it's already impractical to have a grid available as a resource. So again, design consideration. Think about how much you can standardize this and put the burden of the integration experience on manufacturers that are UL rated that will simplify how much and what you have to do on site. Okay, do a little time check here. Storage sizing. So again, this is something that typically I'd spend 10 to 15 minutes on alone, and I think in your design process will be a multi-hour exercise, but we'll try to cover it a little more quickly here. So the battery needs to store enough energy to power the loads when there's no production, and also to average out weather conditions, days of autonomy. For most of the systems that we see that come across our desks, we're looking at 2 to 3 days autonomy. When PV was expensive, this was 5 to 7 days or more. As PV has gotten less expensive, so that's the trade-off we talked about. Let's have less storage. Let's overcompensate with more PV. A system without generator backup, this needs to be much longer, obviously. So the trade-offs of, well, what's a day's autonomy in storage cost me? What's a day's autonomy by just creating more headroom via PV? And then think about the generator. Am I thinking about a smaller generator I've got to rely on more often, or a larger generator that I can run for maybe 8 hours a year that will cover all of my loads for a total of like a 3-day period? As little as 1 day autonomy can be used, but it will be hard on the battery and require substantial generator use.
That's a question of how much PV are you throwing at the system. But you know, if you're planning one-day autonomy and you've got, anytime you've got large generation, large load, small battery, you're going to cycle the battery more frequently, which, you know, depending on which chemistry you pick, maybe is part of the trade-off you make. Talk there about PV sizing. Let's keep rolling. Talking about storage sizing and siting, you know, we'd be remiss if we didn't talk about temperature effects. So capacity on the chemical storage side is almost always reduced with lower temperature. The charge and discharge rates should be reduced at lower temperatures as well. On lead acid, you know, it can withstand -40 when fully charged. That's not anything I'd want to be close to or have to design around. Flooded AGM can make a little difference. They don't survive freezing. Lithium, not a good idea. Takeaway here on the low side is, you know, your batteries need to be insulated at a minimum or conditioned space if you've got conditions like this. On the high side, lead acid lose half their life for every 13 degrees Fahrenheit higher average temperature, operating temperature. So, you know, again, put your storage in conditioned space if you can. If not insulated, lithium is better, but they're best when they're kept at, you know, kind of wine cellar to room temperature. Okay, again, a slide we could spend an hour on, storage types, and I've tried to make put some emphasis here to kind of, you know, trigger a few key messages. Flooded lead acid, it's a robust kind of storage, really high maintenance, must be regularly fully charged. So if it's a system where you anticipate you'll spend, you know, several days at differing states of partial state of charge, not the greatest idea. I mean, you can get close to that with some of the more expensive flooded chemistry, but I think most of the industry has migrated away from that towards the remaining three things on here. So AGM or gel, very low maintenance, can have really good cycle life, must be regularly charged. So in a renewable application, typically not an issue. Just depends on, you know, your outlying hours of the year where you're talking about, you know, you're not getting a full charge because there's not enough generation, then you're in that kind of days of autonomy state. Should be part of your consideration on your chemistry here. AGM with carbon enhancement, so in years past the nanocarbons, now the TLC, some of the other batteries we see out there. Great partial state of charge operation, reduces sulfation, you know, really good cycle life here. This is a great all-around, you know, renewable battery. Tubular gels, seeing a lot more traction on this now that we've got some more options out there and we're getting a little better understanding of what these do and how they perform in some of these applications. Very high cycle life, again, requires a full charge, very low maintenance, and can be found in some really high capacity, call them kitted solutions. So really an interesting chemistry for this type of application, in my opinion. On the lithium side, you know, most of the lithium product that we see for this sector is smaller footprint that you're going to parallel into into larger systems. Almost all lithium iron phosphate. It's a very safe chemistry. It's got good round trip efficiency, really good cycle life. Expensive is the trade-off, but you're making that long life trade-off. So again, we talked about levelized cost of energy. You know, don't just do the data sheet math that says I've got this many amp hours. It's going to cost me these dollars. Therefore, you know, this dollars per amp hour. You've got to think about what's your long-term use case for this project. How often does your, you know, property manager, homeowner, facility guy, you know, person, how often do they want to make, you know, storage decisions and, you know, kind of put new tires on? If it's less, then, you know, you're going to want to lean towards something like this, or at least take a look at it and kind of do the Some other solutions we see out there, the nickel manganese cobalt, the other cobalt variants, see that a lot more for energy management, not so much for the large load shifting and off-grid applications. Needs more complex battery management, needs active cooling, a lot of those things. Less expensive perhaps than lithium iron phosphate, but for this application, you're going to see fewer valid, viable options. And you're not going to see a lot of what I would call great integration capability. Other stuff we see out there, other lithium ion chemistries, we see them every couple months. Somebody new seems to pop up. I don't see nickel cadmium a lot. Nickel iron, there's a couple, really good manufacturers of that, but again, it comes down to what's your threshold and what's your pain tolerance, I guess, on maintenance, and how active and involved in the system operation and maintenance does, the on-site people, how long do those people, how interested and skilled are those people on site? Okay, wow. So we're to our question slide, and I don't know how many questions there are that can be answered easily in this format versus questions on, hey, where can I find more about this? How can you help me with this project? We're eager to take on all of those, so please reach out. Caitlin,